All right. Let's just start it. I mean, we have one more hour, and then we'll finish the week two part of it now in the next 1 hour. So now I'll be talking about like let's say week two. So now I'll be talking about the sinusoids, periodic periodic signals like real real sinusoids or complex sinusoids, and then we'll talk about the periodicity of the signals and fundamental period, the number of unique signals that we have, and all that, right? So yeah, let's just get into it. So let's talk about discrete time sinusoids. The real case. So x of n is, let's say, a cos omega naught n plus theta, right? So phi belongs to minus pi to pi or 0 to 2 pi. Why is this in the sorry some people, yeah. So before going to this, let's say we have a continuous time signal, right? Continuous, sorry, people are joining now. Okay, yeah, continuous signals that we have, like let's say sine omega t that we have. So this is a continuous time signal, continuous time sinusoid with frequency omega, right? Now if we keep increasing omega naught, we get a faster and faster increase, omega increase, we get a faster and faster signals, and we can keep on increasing the signal, keep on increasing the frequency. But in the case of a discrete time signal, this is not possible, because after a point the signal repeats itself basically. So if I want to explain it with let's see, 1 second. So like if we have a signal x of t is equal to, yeah, sine omega naught t again, x of t plus t is equal to sine of omega naught t plus capital T. So this is equal to sine of omega naught t plus omega naught capital T, right? If this is a multiple of 2 pi k, then in that case it is equal to sine omega naught t, right? So this is always periodic with t is equal to 2 pi by omega naught. If t equal to 2 pi by omega naught, or a multiple 2 pi k by omega naught into 2 pi into k by omega naught, what you left with is 2 pi k, which is the individual multiple of 2 pi. If this is an integer multiple of 2 pi, then it is again equal to this. So a real sinusoid signal is a continuous sinusoid, real continuous sinusoid signal is periodic with 2 pi by omega naught. So as omega naught increases, the t decreases. But this is not the case with discrete time signals. So let's say we have sine omega naught n here. So n belongs to integers. So now let's take a capital N, like n log is to capital T. Now let's take a capital N. So in that case, sin omega naught n plus capital N, which is equal to omega naught n plus omega naught capital N, right? Now this omega naught capital N, so n is an integer here. So if this omega naught capital N is equal to 2 pi k, some integer multiple of k, which implies n is equal to 2 pi into k by omega naught, or we can write omega naught is equal to 2 pi into k by n. So here n is an integer and k is an integer. In that case, it is a rational signal. So 2 pi into k by n. If this is of this form, then omega naught is a periodic signal. I mean, this sin omega naught n is a periodic signal. Let's say, this is the, we are talking about the fund. So here t comma n are, if k equal to 1, t comma n are fundamental periods. So I was telling that in the discrete time case, you cannot keep increasing the omega naught and the signals repeat itself after a certain amount of time. What does that mean? So let's say sin omega naught n we have, and then if you increase omega naught by 2 pi, so omega naught plus 2 pi into n here is equal to omega naught n times 2 pi n. Here n is an integer, so since n is an integer, 2 pi n is an integer multiple of 2 pi, which is again equal to omega naught n. So basically in the discrete time case, signals repeat itself, they repeat after 2 pi intervals, right? So this omega naught and omega, so sin of omega naught and omega naught plus 2 pi, so on omega naught plus 2 pi k, all of these are indistinguishable, are indistinguishable. So that is why we restrict the range of the signals to minus pi to pi. Why minus pi to pi? I'll just talk about it in a minute right now. So but why does this not apply to the real case? Because sin omega naught t is not an integer multiple of 2 pi. Only sin omega naught n is an integer multiple of 2 pi because n is an integer, correct? So that is why. So in the discrete time case, they repeat after an interval of 2 pi. Now let's get back to the old case where we have x of n is equal to a sin omega naught n plus phi, right? And then phi is equal to minus pi to pi or 0 to 2 pi, which is the phase. A greater than 0, omega naught is also greater than 0, let's say. Equal to 0, because let's say cos theta is equal to cos of what, minus theta. So if we have cos of minus omega naught n plus theta, for example, omega naught is negative, but this is also equal to cos of minus omega naught n plus theta because of this property. So now again what we have is omega naught n minus theta. So if we can tolerate a phase difference, this omega naught can always be positive. So that is why in this case we restrict the values of omega naught to 0, positive values, but then we can also restrict to any guesses with this, with respect to this, and with respect to this? What is the value of omega restricted to in this case of a real sinusoid? Anyone? Anyone?
0 to 2 pi.
Sorry, can you tell it a bit louder, please?
2 pi.
2 pi. No, it is actually pi. 0 to pi is sufficient here, because let's consider the case from 0 to 2 pi. Okay, let's consider the case 0 to 2 pi. No, so what I've said earlier is can restrict the value from minus pi to pi. This is what you're considering, minus pi to pi. But if in the case of minus pi to pi, again we are seeing here that positive values of omega are sufficient. Even if we have a negative value of omega, that can be brought to a positive value. So this minus pi to pi can be brought to 0 to pi. So that is why in the case of real sinusoid, real cosine omega naught theta plus phi, and plus phi, omega naught belonging to 0 to pi is sufficient. So let's now just consider omega naught minus 2 pi k for k belonging to an integer, right? So but choose k such that omega naught minus 2 pi k is equal to omega naught dash between minus pi and pi. So whatever might be the omega naught, we can bring that omega naught by adding or subtracting a value 2 pi k for any value of k, such that the final omega naught dash will become minus pi to pi. Will be so there is an entire range of signals minus pi wherever the frequency might be, we can bring it back inside by adding or subtracting 2 pi k, correct? So we need to choose one such k. Now cos of omega naught n plus phi equal to cos of, so if this is the case, then what is omega naught dash? It is omega naught dash plus 2 pi k, is it? So omega naught dash plus 2 pi k into n plus phi is equal to cos of omega naught dash n plus 2 pi k n plus phi. This is an integer multiple of 2 pi, so what we have is omega naught dash n plus phi. So any omega naught can be brought into an omega naught dash range between minus pi and pi. So whatever we have, so we started from an omega naught n, we ended with omega naught dash n, where omega naught dash is between minus pi and pi. But let's say omega naught dash is between minus pi and 0. So we bought from minus pi and pi. So this is minus pi to 0 to pi, right? So let's consider about this case. So if omega naught dash belongs to minus pi to 0, then cos of omega naught dash n plus phi is equal to cos of minus of omega naught dash n plus phi. Sorry.
Sir, you muted your mic, sir.
Oh, I'm not. Oh, oh, it's not audible all this while.
No, no, sir.
How long has it been?
Uh, cos omega naught n plus 5.
Oh, just here.
Yeah, sir.
Okay, okay. So yeah, that's what. So we have an omega naught. Oh no. Yeah. So what we started from omega naught n, but then eventually we ended up at omega naught n, but then eventually we ended up at omega naught dash n, which again is in the range of minus pi to pi. So whatever omega naught n might be, we can bring it to this minus pi to pi range. Correct. So yeah, I'm just checking if the recording is working. Yeah. So let's say you have an omega naught and then you bought it to omega naught dash, which is in the range of minus pi to pi. Let's say this new omega naught dash n is in the range of minus pi to 0. So omega naught dash n plus theta is equal to so cos of theta is equal to cos of minus theta. I'm just applying the principle here. So this will be cos of minus omega naught dash n minus phi. Correct. So this equal to minus phi, because so if you have a minus 0.5 pi, we can get it to 0.5 pi, but there is a change in the phase. That's it. So whatever is the frequency in the range of minus pi to 0 can also be brought to 0 to pi. So that is why any value. So what we first discussed is that any frequency in minus infinity to infinity can be brought to minus pi to pi. Now this from minus pi to pi, again we have seen that we can bring it back to 0 to pi only by simple arithmetic operations that we have. Correct. So that is why in the case of a cos omega naught n plus phi, this omega naught is in the range of 0 to pi. Clear? Any doubt?
No, sir.
Sorry? No?
No, sir. No, sir.
Yeah, okay. So now we have seen the real sinusoid case. So let's go to the complex sinusoid. Now let's say complex exponentials. Okay. So after I teach complex exponentials, I'll give a few examples, then it will be clear about how to bring this, right? So let's say we have x of n is equal to e power j omega naught n plus phi. So this is a complex exponential that we have now here, right? So this, due to Euler's theorem, it is cos of omega naught n plus phi plus j sin omega naught n plus phi. Correct? N belonging to an integer. Now, as in the case of real sinusoid, we bought omega naught. In the case of real sinusoid, omega naught is in the range of 0 to pi. But in the complex case, earlier we had only one cosine term. So that is why we could, due to this relation, we could bring minus pi to pi to 0 to pi. But here we do not have that because we have a cos and a sine term. Right? So in this case, omega naught belongs to minus pi to pi. So in the real case, omega naught belongs to 0 to pi. In the complex case, omega naught belongs to minus pi to pi. Right? Let's just do the same proof that we have done earlier for the real case, and then let's see what happens. So like again, take omega naught dash equal to omega naught plus 2 pi k, and then choose k such that it is in the range. So choose k. Sorry, what did I do? Oh, yeah, I mean same case. we have an omega naught 2 pi k, and then we have an origin, so we have a new frequency omega naught dash. So this omega naught dash is equal to omega naught plus 2 pi k. So here omega naught belongs to minus pi to pi, right? So e power j omega naught dash n plus phi is equal to e power j omega naught plus 2 pi k n plus phi, which is equal to e power j omega naught n plus 2 pi k n plus phi, which is equal to e power j omega naught n plus phi. So you're seeing that omega naught is in the range of minus pi to pi. So this is what we have proved in the earlier case also. Omega naught can be brought to minus pi to pi, but due to the real cosine case, we could further bring it down to 0 to pi. But in the case of complex case, we cannot do that because we have two cos and sine terms that we have here, right? So like summarize to again, like summarize once again. We have, in the case of cos omega naught n plus phi, omega naught belongs to, so whatever signal you have, like for example you have cos 2000 pi n 2001 pi n plus phi, this can simply be brought to cos 2001 pi n minus 2000 pi n. I mean this is equal to 2 pi into 1000, right, plus phi, and this can be brought to pi n plus phi. So we have brought cos 2000 pi n to cos pi n. So this is what I was talking about. So any omega naught n in the real case can be brought to 0 to pi. J omega naught n plus phi, similar case, can be brought to omega naught between minus pi and pi. Here also again, whatever omega naught that you might have, you can simply bring it to minus pi and pi. Clear until this point? Is the concept clear now?
Yes, sir. It's clear, sir.
Yeah. Okay. So the frequency, this omega naught, is in the units of radians per sample. So if we draw a range of signals 0, pi, 2 pi, minus 2 pi. Let's talk about low and high frequencies here. Okay, so if we take a real complex exponential or real exponential, if omega naught equal to 0, x of n is equal to cos 0 equal to 1, which is a DC signal. But if omega naught increases from 0 to pi, oscillations increase. 1, 2, 3. Let's say omega naught is at pi. In that case, x of n e power j pi n is equal to cos pi n is equal to minus 1 power n. So it's like at each sample 1 minus 1 1 minus 1. This is like the highest frequency that we can have in the discrete case. So at 0 it is a 0 frequency signal, at pi it has very high frequency, but then if omega naught changes from pi to 2 pi, this is a beautiful case where oscillations decrease. Oscillations are slower. I mean they are decreasing again. In the continuous case, once we are going from the real, when we are increasing, they keep on increasing. But here, if you see, this is like discrete time is so beautiful that it is only restricted to a certain range. Until this point it is increasing, but then from here it is again decreasing. If I say, if in this here, if I say the oscillations oscillations, they are increasing, and then at one point it is again decreasing, right? And then again, if we say omega naught equal to 2 pi, then x of n is equal to e power j 2 pi n is again cos 2 pi n plus j sin 2 pi n equal to 0. Again we have a DC signal where oscillations are 0 again at 2 pi. Similarly, here it just repeats itself. Not okay, sorry, that was 10 minutes ago. Okay, yeah, so this concept is clear, right? So in the range from minus pi to pi, from minus pi it is increasing, it is decreasing, from 0 again it is increasing. So this range of values around minus pi are called high frequency, and this range around 0 and 2 pi are called low frequencies, right? Isn't it nice? Because in the continuous time case, there is no such rule like this, and then you have to, like, for example, you have a frequency domain where, so someone is joining, yeah. So in the continuous time case, there is no such thing as repetition. So it can be like increasing, decreasing, it can be random. The signals which we have, right? So there is no such case. You have to like store everything. Like if you have a real signal, real continuous signal that you generate, and if you see the Fourier domain, the frequency domain, the frequencies that it composes of, it can have a, if this signal is finite length and it has frequencies over the entire range from minus infinity to infinity. If it is finite length, bandwidth belongs to entire minus infinity to infinity. Is it even possible to store this signal? No, because we have an entire range. Like what we are concerned in the real domain is like, what you actually want to work on is real continuous time signals. But can we store them in a computer? Can we do any computation on it? No, because there are infinitely many bandwidths. But in the case of a discrete case, if you bring it to the discrete case, now the frequency domain repeats itself in the range of 0 to minus pi to pi or 0 to 2 pi. So now if you want to store this in a computer, you can just simply store these values here. These range of values here, which is far more easier to do. Correct? So this is a beauty of the discrete time case. But yet again, this again is a continuous. Yet again, this is continuous. So again, it is not. We are not able to store that. Just so this is a far later part of the course where again this also is sampled, and then only samples of these are stored in the samples of the frequency domain are also are stored. So this is known as the DFT. This is taught like way later, like a lot later. So this is DFT. So let's just take a detour. Let's see the beauty of this. So what have you seen here? We have a continuous time signal. We sample this in the frequency domain. It is getting periodic. Correct? Earlier this continuous time case had a frequency domain something like this, had all frequencies, but if you sample this, you get a periodic. But then what if you sample here? Similar thing happens here. This gets repetitive. This is again week 10, week 11 course, week 11 subjects. I'm just like showing the importance of why one of the many benefits of why we do this discretization working with digital domain. Right, so let's get back to this. So what was I talking? So I was talking about 0, pi, 2 pi, minus pi, minus 2 pi. So this range of values are low frequencies, and this range of values, these are low and these are high frequencies, right? So this is the low high frequencies of the omega naught, the range of values of omega naught for real and the complex cases. Any doubts until now, until this point? So in the real case, omega naught is in the range of 0 to pi, and the complex case we have from minus pi to pi. Is this clear?
Yes, sir.
Any doubts? Anyone?
No, sir.
Anyone has any clarification or anything? No one? Should I continue?
Yes, sir. You can.
Okay, yeah. Okay, so let's just let's talk about. Okay, why don't we do some examples? It'll be nice. So let's say, so we have a signal cos omega naught n. Okay, and we need n which is periodic. I mean, we need to find if it is for different values of omega naught, right? Is it periodic? If yes, what is the period? This is the question that we have, right? Let's say omega naught equal to 0.2 pi. So cos of 0.2 pi n. If it is periodic, what is the case? 0.2 pi n plus n. Let n is the period. So 0.2 pi n plus n, which is 0.2 pi n plus 0.2 pi capital N. Correct? So this should be an integer multiple of 2 pi k. So 0.2 pi n is equal to 2 pi k. So n is equal to 2 pi into k by 0.2 pi, which is 10k. So the least value of k for which kn is an integer, so least integer value of k for which n is an integer is k equal to 1 and n equal to 10. So n equal to 10 is the period of the signal cos 0.2 pi n. Okay, let's take another example, cos 0.9 pi. So cos 0.9 pi, right? So similarly, again we are stuck with this case where 0.9 pi into capital N is equal to 2 pi k. N is equal to 2 pi into k by 0.9 pi, right? So anyone knows the values of k and n? What is the least value of k for which n is an integer? What is the least integer value of k for which n is an integer? Give it a try. Anyone?
1.
Value of n equal to 1 or k equal to 1? Anyone else? Anyone? Are you guys there? Alright, okay. So if we take k equal to 9, so 2 into 9 is 18. In that case, n equal to 20. So n, this is the answer. N equal to 20 is the period of this signal. Let's take omega naught equal to root 2. Let's have some. This is interesting, right? So omega naught root 2n. Root 2n. So here n is equal to 2 pi into k by root 2, which is root 2 pi k. So What are the values of k and n? I need everyone to be like responsive so that it will be more interactive. It'll be interesting for you guys too. Anyone? Alright, so this actually there is no value of k that exists for which n is an integer. So this does not exist. So this is actually not periodic. So this cos root 2n is not a periodic signal. Right? Yes, I think someone has answered. By I should have waited 2 more minutes for Deepa. Yeah, yes, Deepa. So this is a not periodic. This is a non-periodic signal. Here we do not have a so we need to make sure that both k and n are integers here. So if they are not integers, we cannot find rational values of. I mean, to k and n should be integers. If we can't find integers, then it is not periodic, right? So this is about the periodicity of the thing. Any question that you want me to solve? Any doubt? Any question that you would like to ask me? You can unmute your mic and ask, and don't have to write it down in the chat box. Okay, let's say like just do one more last one, and let's see if anyone. It'll just be an easy one. Cos pi by 19n. What is the value of k and what is the value of n? I'll give it a minute. Right, let's see. I mean, you can either unmute or you can put it in the chat box. I suggest you guys to try solve them because it would be helpful for your quizzes anyway. These type of questions would be there in the quiz. Yes. K equal to 1, n equal to 38, and 18 or 38? 18. No, it's actually k equal to 1 and n equal to 38. So if you say n equal to 2 pi k by pi by 19, so pi a equal to k. So if you put k equal to 1, n equal to 38. So n equal to 38 is the period of the signal. Yes. Yes. So k equal to 1 and equal to 38 is the right answer. Yeah. So let's just move to another type of question. So where question 2 would be. Sorry, I think some person has left and joined it. So Akhil, so this is the answer. K equal to 1 and n equal to 38 is the answer for that previous question. So let's say now the question let's see another type of question where we have a signal cos omega naught n plus theta. Sorry, we have the previous one that is solved. So we have a signal of cos omega naught n plus theta. We need to bring it to cos omega naught dash n plus theta plus or minus, or let's just plus theta dash, where omega naught dash n is in between 0 and pi. This is what we need to solve. So we will be given a question, and then we need to bring the omega naught between 0 and pi. Okay, so let's try one question where cos of 1.6 pi n. So this can be done as cos 1.6 pi n minus 2 pi n, right? So cos, which will be cos minus 0.4 pi n, but then again this should be equal to cos 0.4 pi n, since cos of minus theta equal to cos theta. So now we have an omega naught dash which is between 0.5, which is in the range of 0 and pi, right? Interesting. So 30 seconds. Let's see if anyone can do this. 0.2, 0.3 pi n. It's very easy. Anyone in the chat box? .3 pi n. It's very easy. I think you just have to do the exact same step of the first question. So this will be cos 2.3 pi n minus 2 pi n, which is cos 0.3 pi n. So 0.3 pi omega naught is 0. Is the answer. 0.3 Priyanka. Then this is 2.3. Maybe I would have this is visible as 2.2. Sorry for that. This is 2.3. I'm sure you might have done the right one. Right thing. It must have been my handwriting. So 2.3 pi n will give you 0.3 pi. Okay. Okay, let's see. Let's see one more interesting one. Sine minus 2.3 pi n plus pi by 3. I need to bring it to cos omega naught n plus phi, omega naught between 0 and pi. Anyone? Like, just tell me the first step. What should I do? You can unmute your mic. So the first step would be to bring it to cos. So minus 2.3 pi n plus pi by 3 minus pi by 2. So which is cos of minus 2.3 pi n minus pi by 6, correct? It. So now just apply minus 2.3 pi n plus 2 pi n minus pi by 6. Again add 2 pi n, so it will be 0.3 pi n minus pi by 6. So omega naught is 0.3 pi, and then phi is minus pi by 6. Is it clear? Anyone has any doubt? Phi program 5 pi by 6 plus 2.3 pi n. Oh, okay. So you want it. Okay. I mean, that is the first step that you saw, program, right? Correct. So exactly. So this is the final answer. Is it clear, everyone? Anyone has any doubts? So all you have to do is, whatever omega naught that you have, find that 2 pi k, find that value of k, so that it will bring it to in between 0 and minus pi and pi. Once you bring it to minus pi and pi, you just have to shift the negative sign because of the cos inequality and bring it to 0 and pi. That is for the real case. In the case of imaginary, simply, I mean, in the case of complex, you can just bring it to minus pi and pi, and that is enough, because in the complex sinusoids, the omega naught are in the range of minus pi and pi. But in the case of real sinusoids, it is in the range of 0 to pi. Clear? One more thing that I wanted to talk about is so symmetry is also one characteristic of a signal. So if a signal x of n is conjugate symmetric, it means x of n is equal to x of minus n. And then if x of n is conjugate antisymmetric, then x of n is equal to minus x star minus n. So this is the thing. So something, and then lastly I want to talk about linearity and time invariance, which are properties of system, not the signal. So until now what we were talking about, the periodicity, real, even, conjugate symmetry, everything is real, I mean it's characteristic of the signal, but now it is a characteristic of the system. So let's say you have a system, sine 2.5 pi n. Raghuram, are you asking, is it a question or do you want me to solve that? So 2.5 pi n, you just subtract minus 2 pi n, you get a 0.5 pi n, that is the answer. Okay, yeah. So here let's say we have a signal x of n, and then we send it to a discrete time system. So I'm like representing this discrete time system, and then y of n, I'm using this notation where x of n t, we get y of n, right? So this is the notation. So linear system, so a system is linear if it is both additive and homogeneous, and it satisfies homogeneity property. So when is the system additive? So let's say you have a system which inputs x1 of t and outputs y1 of n, and then inputs x2 of n and outputs y2 of n. So if you add x1 of n plus x2 of n, the output should be y1 of n plus y2 of n. So this is if this is satisfied, then it is a additive system. Homogeneity is when if you give a signal x of n and produces y1 of n, and if you multiply it with a constant, then it should give alpha of y1 of n, and then it's satisfies homogeneity. If it satisfies both, so this is b, yeah, both a and b, then it is linear. This is one thing. So this is the linearity. And then one more thing would be time invariance. So let's say you have a signal x of n and the output is y of n. Now if you delay the signal x of n by x of n minus n naught, the output must also be delayed by n minus n naught. This is known as a time invariant signal, right? So this is linearity and time invariance. So there are this type of signal systems called LTI systems, which are both linear and time invariant. So last 5 minutes I'll just give one example with time invariance, linearity and time invariance, and then we can just leave. So one more, so let's take a system where if we give x of n to a y of n would be x of 2n minus 1. What about this fourth? Any idea how to do this? To n minus 1. So this is a, so if we give x1 of n, it would give y1 of n is equal to x1 of 2n minus 1. If we take x2 of n, it would give y2 of n, which is equal to x2 of 2n minus 1. So if you add both, you get a additive system, and also if you do alpha of x of n, we get alpha of y of n, which is equal to alpha of x of 2n minus 1. So this is a linear system. Let's see time invariance. If we give x of n, we get y of 2n minus 1, right? So if we give n minus n naught, what should it be? Is it y of 2n minus 1 minus n naught? Why is it not working? So this one, is it right? Anyone, yes or no? No, this is actually wrong. So it should be, as I mentioned earlier, during the shifting and scaling, the shifting is only done to the independent variable. So it should be y of 2 of n minus n naught minus 1, which is y of 2n minus 2n naught minus 1, which is not equal to y of 2n minus 1 minus n naught. Hence it is not time invariant. So yeah, this is the case. So whatever you're doing, shifting or scaling, you apply it only to the independent variable, correct? So only if you apply to the independent variable, it is, then you see if it is variant or time invariant. It is, here it is not time invariant, right? And then there is one more thing called causality. So is this signal causal? Is the system causal? So okay, I mentioned causality about property of signal, but causality about property of system is, a system is causal system is when if output y of n depends only on input at n dash less than n. I mean, it depends only on that, on the current, that is only on current time and past time samples. So this is causal signal. So if you see here, y of n is equal to x of 2n minus 1. Is this causal? Yes, it is causal, because this depends only on the, sorry, it is not causal. because let's say y of 1, in that case x of y of 3, for example, in that case it is x of 5, which is depending on the future sample. So non-causal. So what if y of n is equal to n times cos of 2n? Is this causal or anti-causal? Sorry, n times x of 2n. Is it causal or anti-causal? Sorry, causal or non-causal? It is non-causal. What about n plus 1 times x of n? Is this causal or non-causal? Last 3 minutes, I'll just end the session. N plus 1 times x of n, is it causal or non-causal? It is causal. But you might be wondering why if it is n plus 1. But we need to see only the inputs of x, not the coefficients. To show the only inputs of n. So y of n depends only on x of n. So it is causal. Right? So yeah, causal, and then there is this something called memoryless systems. So all memoryless systems are causal. Basically, memoryless systems means that y of n depends only on x of n, that is depends only on current time instant. So this is a memory system, and then there is last thing is bounded input and bounded output. Bounded input, bounded output system. So if we give an x of n and produce a y of n, if bounded input, bounded output, so if this x of n is less than infinity, then mod y of n should also be less than infinity. Then it is a bounded system. Right? Any doubts so far? So I think maybe we can like end it here. If you have any doubts, you can ask it. Or else we can end this session here. Okay. Okay. All right, guys. Thank you for attending. If you have any more doubts, you can put it up in the forum always, and we will be able to. So we will answer them in the discussion forum also. Thank you so much. Thank you for attending the lecture. Thank you. You may leave now.
Thank you, sir.
Thank you. You may leave the meeting.